So, as we said, today's lecture will be the media access control sublayer. Why we said sublayer? Because it's a part of the data link layer. It's not the whole data link layer. Media access control, or MAC for short, is of course, as we said, to handle the access to the media. We can consider the data link layer as two sublayers. The upper sublayer, which is data link control sublayer, which is responsible for flow and error control, and it's called logic link control or data link control sublayer. We mostly refer it as LLC, logic link control. The lower sublayer, this one is the one that we study today, is responsible for resolving access to the shared media, as we said, and it's called media access control or MAC sublayer. But as we said, if you have two links, two nodes and a dedicated link between them, then you don't need this sublayer, the MAC. You just need the data link control sublayer or logic link control sublayer, LLC. So how to manage the access to the shared media? Actually, there are many protocols to handle this issue. So we'll study some of them in this lecture today. So when we have many nodes or stations that are connected together using a common link, as like when you have, for example, the bus topology, there are many links connected to that bus. So we need a multiple access protocol to coordinate access to the link. There are many protocols to handle access to the shared link, and all of these protocols belong to the MAC sublayer. So they are all here in the MAC sublayer. Okay, all these protocols. We can categorize them in three groups. So the multiple access protocols handle the access to the shared media. We can categorize them into three categories. Channelization protocols, like we'll not study these because you'll be studying them in a different course, wireless communication. So we have FDMA, frequency division multiple access, TDMA, time division multiple access, and code division multiple access, CDMA. These protocols are called channelization protocols. We have the random access protocols that we study in this lecture, and include Aloha, CSMA, carrier sense multiple access, CSMA, CD, collision detection and collision avoidance protocols. And we have the controlled access protocols. There are three categories: reservation, polling, and token passing. We study all these in this lecture, but we'll not study the channelization because, as we said, you'll study them in a separate course. Just a short description of the channelization protocols. In these protocols, each user allocates its capacity by using one multiplexing scheme. So, for example, FDMA, TDMA, whatever multiplexing scheme. So TDMA, for example, or FDMA, you have the frequency. So this frequency will be allocated to, so you have the bandwidth. So this bandwidth is now allocated between for the 3 users. So each of them is allocated this amount of the whole bandwidth. For n users, the bandwidth, of course, if you have 10 users, the whole bandwidth will be divided by 10 for each user. So if you have here you have 3 users, the whole bandwidth will be divided by 3 for each user. So we'll use 1/3 of the bandwidth available. There should be no interference between the users. Actually, there are issues, of course, when the bandwidth overlaps. You see here's crosstalk, so we have to avoid this. You'll study these issues actually in the wireless communication course. One example is FM radio, frequency modulation stations. When there are many users, a large piece of valuable spectrum or bandwidth may be wasted. Why? Because you see, if you do, you need to prevent this crosstalk. So normally you may do this bandwidth, for example, is wasted. This another bandwidth. So even though the bandwidth is divided between among the users, there's still some waste, and you don't make use of the bandwidth. You need to avoid crosstalk and interference between the channels. If more than n users want to communicate, some will be denied permission for lack of bandwidth. So sometimes there are many users that want to communicate, but the bandwidth is only, for example, can accommodate 3 users at a time. So if there is another user, you should wait until this user or another user is out or stops using the channel, then he can. So in this case, even if some of users, for example, this user only transmits very limited amount of data, but because is still accessing the channel, the other user cannot use it. He should wait until some of them or some slots in the channel are available so that they can start their communication. Therefore, in this channelization protocols, we normally don't make use of full available bandwidth. So the other category, as you said, is random access protocols. So all these categories are for handling the access to the shared media. So in random access or contention methods, contention or random access we call them, contention-based protocols, no station is superior to another one, and none is assigned the control over another. So any station can, it has all the functionality. There is no like server and client or host and access point. A station that has data to send uses a procedure defined by the protocol to make a decision of whether or not to send. We have 2 features that give this method its name. So the name came from these 2 features. Transmission is random among the stations, hence the name random access. Okay, so you cannot you should not be able to predict when when the transmission will happen or which station will do the transmission next. Okay, no rule specify which station should send next. Stations compete with one another to access the medium. That is why this method is called contention based. So you don't know which station will access the channel next. They all compete or try to access that channel, but maybe one of them will succeed, the other ones will not. This is why it's called contention based. So these are random access protocols, contention based methods. When more than one station tries to send, there is an access conflict or collision. This is an important issue that we need to handle when there is this happens. So what's a collision? Collision, for example, this station and this station are sending data. So data is 0, 1, of course. So let's say, and these data will travel across the channel. Channel can be any link or wireless or whatever. So if at some point they collide, that means, you see, if this one collides with this, then the signal will be something like this. So if, let's say, normal logic, 0 is 0 volt and this is 5 volt. When a collision happens, you see, there will be nearly 10 volt. So how you detect collision? If you have signals that are higher than the normal value, peak values. So if it's 5 volt, you sense the channel, you see 5 volt signals maximum. You think there is no collision, but if you sense some signals with 10 volt peak, then you are sure there is a collision happened. Two signals from two stations collided to make this. Of course, there can be different patterns of collision, but the way you detect is that there are signals with higher voltage, peak voltage values. Okay, so to avoid access conflict or resolve it when it happens, each station follows a procedure that answers the following questions. So we want to prevent or to avoid the access conflict, or if it happens, to resolve it. So we need some procedures. When can the station access the medium? Okay, so you have to answer this question. The protocol that you are devising to access, to manage the control or the access to the channel should answer this question. When can the station access the medium? Okay, what can the station do if the medium is busy? So you try to access the medium, but you sensed it and you saw it's busy. How you check it's busy? If there is, you are not sending, you're just listening, and you see there are some data coming, that means it's busy. How can the station determine the success or failure of a transmission? So if you send a packet or data, how you check if this data arrived at destination or not? Okay, so this also the protocol should answer this question and have mechanism to check. What can the station do if there is an access conflict? Access conflict means what? Collision. So if collision happens, we detected high levels of voltage. What should you do? So the protocol should answer these questions, the random access protocol. So if we go back here, the random access protocols that we study is are Aloha, CSMA, CSMA CD, and CSMA CA. So we study these one by one. The simplest protocol is Aloha. Aloha was developed at the University of Hawaii in 1970 for radio or wireless LAN. There are potential collisions as medium is shared between the stations. So you have many stations, and there is the media, which is the wireless medium. It's shared between all these stations. The original Aloha protocol is called, okay, so we have this pure Aloha version, okay, the original Aloha protocol. When two or more stations send data at the same time, collision will happen and collided frames will be destroyed. So you see here, for example, station 1 and station 2 at this time, you see their data, this was sending and this was sending at the same time, so there is collision here, so the data is destroyed. Collided frames should be resent, so this is destroyed, this is damaged also, so this station 1 should resend this frame, station 2 should resend this frame, because why? These frames were destroyed, but frame 1.1, for example, didn't collide with any other frame. Look, it didn't collide with any other frame, so this is fine, you don't need to. But this one collided and you need to resend it. Station 2, for example, need to send this one, and because here also this one collided, so this one also should be resent. Station 3, this one collided with this frame and with this frame, so this one is damaged. Station 4, and so on. So if a collision happens, you should resend the data or the frame. This is the Aloha protocol or the original Aloha, which we call pure Aloha protocol. Pure Aloha uses acknowledgements, okay? So this is to answer what? If we go to our questions, we said that what can the station do if there is how can the station determine the success or failure of transmission? So to answer that, Aloha uses acknowledgements, okay? If acknowledgement does not arrive after a timeout period, the station assumes that the frame or the acknowledgement has been destroyed and resends the frame. So when this frame, you send this frame, okay, how you check that this frame was delivered properly to the destination? The destination should send you an acknowledgement, okay? So if you receive the acknowledgement, that means the frame was delivered successfully. But sometimes the station, the receiving station, when sends the acknowledgement may be will collide with another frame, so it will be destroyed. So you may need to resend the acknowledgement also. When the timeout period passes, you have to wait, because when you send the data here, you send this frame, the destination is here. You have to wait for the acknowledgement until you can say this data was delivered successfully or not. So how long you have to wait? This frame needs time to propagate from here to here, okay? And if it arrives successfully, this station will send acknowledgement. This acknowledgement will also need time to go back. So this is the time that you need for acknowledgement to arrive. So when the timeout period, what we mean by timeout period, this is the timeout, here to here and from here to here. So you have to wait this time. If this time passes, each station waits a random amount of time before resending its frame. So if this time passed, you are not going to send instantly. You have to wait a random amount of time before sending your data. After a maximum number of retransmissions, the station must give up and try later. So if you sent a frame and you waited for the timeout and then a random amount of time, and then you tried again, and then you didn't receive acknowledgement, then you tried again and again, many times you tried and you were not successful, you'll give up. You say there is something wrong, there is too much traffic, then I'll wait and try maybe after 2 minutes or something like that. So this is how Aloha works. The timeout, so this is the timeout that you have to wait before calling your random, is the maximum possible round trip propagation delay. Okay, so if you have many stations, so these stations are connected like, let's say, a bus topology. Sorry, because so what's the maximum possible round trip time here is, if this station sends something to here, this is the maximum time, and if this sends the acknowledgement back, so this is 2 times the required time to send a frame between 2 most widely separated stations. So this is TP, okay, TP times 2 is the timeout period. So TP is the time period from the for the frame to propagate from one station to the other furthest station. So the two most widely separated stations, TP is the time for a frame to propagate from one of these to the other one. The back of time is a random value that depends on k. We'll see the algorithm in the next slide. So k is the number of attempted unsuccessful transmissions. So when we sent this frame, for example, or this frame, and it was not successful, we'll try again. So we increase k. K was 0, for example. Now we can make it 1. If we try again and it was not successful, we make k 2. If it tried again, and so on. So the random, the back of time, TB, depends on k. K is the number of unsuccessful attempts. One common formula for k is to use the binary exponential backoff. So you can say, to find TB for each retransmission, and random number is chosen between 0 to 2 to k minus 1. So you every time, if it was the first attempt, for example, k is 1, so 2 to power 1 minus 1, which equals 1. So you choose a random number, either 0 or 1 here. But if k was, for example, 4, 2 to 4, which is 16, so you choose a random number between 0 and 15. So in this case, it can be 0 or 15 or 13 or 9 or 7, whatever number. Okay? So you find this TB, which is a random number between 0 to 2k minus 2 to power k minus 1, and then multiplied by either TP, as we said, is this is the TP, the maximum propagation time, or TFR. TFR, the average time required to send out a frame. So it's the time, average time actually, to send a frame. So you either multiply it by this or this. So this is the pure Aloha protocol. So a station has a frame to send. What it should do? You have a frame you want to send. Firstly, you set K, because you didn't try, this is the attempt, you set K to 0, okay? Now, you want to send a frame. Send a frame, okay? Send a frame, don't sense, don't do anything. Send a frame. Wait timeout. Timeout is why we said we need to wait this time, because the frame needs time to propagate to the destination and then the acknowledgement to arrive from the destination to the sender. So we have to wait this time, 2 times TP. TP, we said the maximum propagation time. So if you receive the acknowledgement, that means you did the transmission successfully. But you may not receive the acknowledgement. Why? Because when you send the frame, it collided with another frame, like here. So I sent this frame, but it collided with another frame from another station. So this destination will receive the frame, but is corrupted, so it will not acknowledge because it was not received successfully. Okay, so either because a collision happened or because this frame arrived here successfully, but then the station sent the acknowledgement. The acknowledgement collided with another frame, so the acknowledgement was destroyed. So the receiver will try to maybe resend the acknowledgement, or the sender maybe will that depends on the protocol. So in this case, if the acknowledgement is not received after 2 times TP, then we'll try again. The sender will not try to resend the receiver, will not try to resend the acknowledgement, but the sender will try again to send the frame. Okay, so that's how the protocol decides. Okay, you may try in this case, for example, because the acknowledgement was